Hi everyone, so we begin now the Wednesday's lecture. Okay, so today we're going to continue to review the solid space in the multidimensional case, but we are going to mainly do some examples only. Okay, so let's recall so let's say that you have omega in Rn. Okay, so the solid space WKP, and this is equals to all the F in LP space, so that they exist weak D alpha F, and which is also in the LP omega, and those multi-index alpha is less or equal to K. Okay, so this is the notation of the solid space. So today we're going to see some examples, and we have seen such an example before in the one-dimensional case, where you can see that there is a function which carries a corner, which is not differentiable in the traditional sense, but however, the function is still differentiable in the weak sense. So we're going to see such example in the multidimensional case. So let's say that this is omega, and this is omega. Okay, so I don't care what the boundary is. It's here is just domain, and I have a function here f, which in the L1. So here we are not talking about the WKB space. We just look at the weak derivative. Okay, so let's say the f is just in our the L1. It's just in L1 for the simplicity. So this is omega. Okay, and the function is defined on this omega, and the function is almost everywhere differentiable except a few points. So let's say you have a finite number of points here. So let's say you have by 7 points here inside the domain, and at those points the derivative of f does not exist. Besides that, the f is differentiable on the entire domain. Okay, so those are the bad points. So at this point, the function may carry some corner, like corner things, like similar to the corner. Okay, in the multidimensional case, the function is not differentiable there. So the something is, let's say that, so let's consider one of the partial derivative of f. So let's say the dj is a partial derivative. Okay, first order partial derivative in the j's direction. Okay. so let's call the z is the connection of all these dots. So I don't have to give a notation of these points. So just denote this z is just a collection of all these bad points. Okay, so this one is in C1 and omega, subtract the z. So this means that at the z, the function is not differentiable. But however, away from z, so away from this 7 point, the function is differentiable, which is continuously differentiable, the dj. Okay. Now for simplicity, let's assume that the dj, overall dj, okay, is bounded. It's bounded by some constant n. Okay, this is a very simple assumption. Okay, now the question here is, so you can see that on the entire domain, and our function dj does not exist as an entire derivative on the entire domain. Okay, but however, it exists on those points which is not belong to the z. Now the question is whether the function is differentiable in the weak sense. Okay, now in the one-dimensional case, we see example before. We see that in that case, the function is differentiable. Like in the one-dimensional case, remember we talked about that. They did a corner point inside the domain AB. Okay, it's just like in this situation. Okay, and the function is still differentiable. And in the one-dimensional case, the same argument can be used to show that maybe you have several coordinates, that's fine. Okay, so here we are dealing with the same question. So we'd like to see that in this case, in the multi-dimensional case, in any dimension, whether this is true or not. Okay, we're going to show that what we are trying to show that this guy, even though it does not, this guy is not in C1 omega, right? You know, in the classical sense. But however, this one exists weakly on omega, on the entire omega. Okay, so that's the result we're going to see. Okay, all right, so let's see how we can prove this. Okay, now you can see that first, let's pay attention to the set Z. Okay, now Z consists of only 7 points, so you can see that obviously Z, this measure equal to 0. There's no problem. Okay, and therefore Z can be belongs to some open set like GM, so that so this is open set, and also the GM goes to 0. The measure of GM goes to 0 as n goes to infinity. Obviously this is true, because why? Because you can see that at this some point I can create this GM by using circles. Okay, using circles around this domain. Okay, so as long as the diameter of the circle is sufficiently small, we can make this guy small than any given number. So therefore, by shrinking the diameter radius of the circles, you can create an open set GM goes to 0, which covers exactly these 7 points. Okay, so this is our approach. Okay, so now in order to have this begin to prove this, we need to remember some theorem. So you have to remember which is called the divergent theorem in the multidimensional case. Divergent theorem say that the integration, suppose you have an f, okay, let's say dj to a scalar function f, a capital F or omega, okay, and suppose the domain is sufficient, I mean the boundary is smooth, whatever, but in this case, I mean we can assume everything because we're using circles only. The boundary this is sufficiently smooth, and the outside boundary we don't have to care, because you remember in the weak derivative definition there's a phi function, okay, the testing function will become 0 from near the boundary. Okay, so you don't have to worry about it. Okay, this divergent theorem say that this derivative, the integration of this derivative should equals to the integration of the boundary of the domain, okay, f times the Vj ds. Okay, so that's a special version of the divergent theorem. Basically, this is a multidimensional fundamental theorem for calculus. Okay, so this theorem, what is mu j? Mu j is basically the normal vector. Like suppose you have considered the outer normal. You consider this boundary, the normal is like this. It's a normal to the boundary, so it's like Vj, V. So Vj is the j's components of this V. So this one is a V1, V1, Mu2 to Mu n. Okay, so suppose you have the boundary inside, like here, on the boundary. Then you talk about the normal pointing to the center. Okay, so this is our 2. That's a divergent theorem. Now we're going to use this divergent theorem, okay? So what we're going to do is we're going to consider now the integration. We're going to consider the integrations on the omega, and then you have the dj, then f times the phi. That's a testing boundary. But however, you can see that the derivative of f does not exist on this special point, so you cannot integrate this guy directly on omega, right? So let's remove this points, but I'm removing the entire GM. I'm removing the entire GM, okay? So once I remove the GM, it's removed all of these points. Okay, and then apply the divergence theorem. Now if you apply the divergence theorem, and you can see that this reduced the boundary, right? But you can see, so where is the boundary here? The boundary of this case it consists of these portions. So that's the outer boundary, right? And also, it's including the circle. So each circle is also part of the boundary. Because integration is really between this big domain and the circle. So you can have many other boundaries. But we don't have to be more notation to denote these things carefully, so that's fine. Okay, so as long as I understand. Now on the outer boundaries, then we don't have to worry about, because the phi will become 0. So integration of the outer boundary will disappear. Okay, we only need to talk about inner boundary. So this means that this is basically equal to on the boundary of GM. Okay, then you can have the DJ, the F, and the V, and the VJ. Yes, it's equal to that. Okay, so but you know that this boundary consists of 7 boundaries together. Okay, all right. So this is our thing. So what we're trying to do, we're going to estimate on the right side. We're going to show that. So we need to show that. So as m goes to infinity, and this guy goes to 0. Okay, so this is what we need to show. All right, and this is very simple, because at a simple estimate. So let's look at the estimate. So on the boundary GM and F, V, Vj. Okay, and DS. Okay, now remember the F is bounded. Our function is bounded, okay? The phi is a smooth function which is also bounded. So therefore, and these two things together is bounded by some constant c. So I can say that this is less than controlled by c, that is moving c out. So it's like this. And then you have a Vj. Vj is a component, it's a unit normal component which is less than 1. The norm is less than 1. So it's basically ds. Like this. Okay, so this term is what basically the total length of the boundary. Okay, and obviously this thing is what? It's less than the 2 pi times the 2 pi times the radial of that, right? 2 pi times the radial. And radial, actually, you can see that as we select the GM, that goes to 0. So this means that the radial itself will go to 0. So therefore, you can see that this guy should obviously goes to 0. As m goes to infinity. Okay, so this means that if we let m goes to infinity, so the whole integration, the right side goes to 0. Because the right side goes to 0, so this indicates the left side also goes to 0. So therefore, so you can see, you can letting the m goes to infinity, okay, and on this left side, and so then you can see this domain, what goes to what? What goes to the omega, right? What goes to omega. So therefore, you can see that this integration, on the whole integration, okay, and dj and yeah, maybe I'm going to write this slightly. Wait a second, okay. All right, so before letting m goes to infinity, so let's work on the right side, okay. So the right side basically is equals to integrations omega minus gm. Okay, you differentiate this, so you get the first thing is f dj phi, and then plus another term omega the gm. Okay, and then you can see using the product rule, this is dj f n times the phi. And then this should equals to, so this should goes to 0 when n goes to the infinity. So this is what we have. Okay, now carefully look at these two terms. So this guy, so you can see that if you let the n goes to infinity, so the first term, this term will just goes to the integration of f dj phi. Okay, and then, so how about the second term? The second term, if n goes to infinity, and then you can see that the dj, okay, dj is the you have to think about this, the LP function. Okay, the LP function, because it's defined on the entire domain except these points. So if you view this LP function, then you can see the djf is well defined. It's just the LP function. Okay, since this guy exists in the L1 sense. Okay, in the L1 sense. So therefore you can take the limit, and then finally you can get this. So you can see if you let n goes to infinity, you will end up with this goes equal to 0. This goes to 0. This is exactly equal to 0. At this equal to 0, this means that the integration of omega f dj and the phi should equal to minus integration omega dj f and the phi. Okay, so this simply means that in the definition of weak derivative, this guy is viewed as L1 function here is the weak derivative. Is the weak derivative. So that's how we prove this is a weak. This function f is weakly differentiable with the weak derivative by the dj. Okay, so no matter how many corners you have, as long as you have a finite number of corners in the domain, then this proof all applied. And actually, sometimes when you have the suppose you have infinite number of corners here, suppose like this. Suppose so these corner point actually accumulated at somewhere. So here's a point, okay, but somehow these corner point accumulated to something, okay, and then this proof still works because you can cover and these points by so you still think about this is the set z, okay, then you can still cover this by a finite number of circles with arbitrary small radius. Then the proof still works, okay, like here. So you can firstly cover this accumulation point by a circle, and once this is covered by one circle, then the rest will be only a finite number of corner points, and then you can cover them by some still by another finite number of corner points, and then you can go through the whole proof. It still works. Okay, so this is one of the example I want to show you. Okay, it will show you how to handle the function which is strongly differentiable except by a few corner points. But here, actually, I made a very important assumption. It's saying that this function f, okay, this function is bounded. It's bounded, which means that even though the function is not differentiable at its corner point, but the function is still bounded. Okay, and in the next example, I'll show you the case where actually the function can be unbounded on this corner point. Okay, now I'm going to show you a simple one. So the second example I'm going to show you is that this is only in the two-dimensional case. So let's think of B1, which is inside the R2. So we have a unit circle, okay? And here we have a point which at this point the function it's not only not differentiable but also it's unbounded. How do we handle it? Basically, we can handle this in the same way. So I'm going to think about specific function here to demonstrate this calculation. I will choose the fx equals to 1 over absolute value of x. Now the x is a vector, so this means the norm of the point. Okay, so it is alpha. Alpha is a power. Okay, so think about this one. You can see that once alpha is positive, this function becomes unbounded at this point, at the 0 point, right? So we're going to see whether this function, how do we handle this function. And we're not just want to look at a weak derivative, and we want to think that this function is in the W, is in the W 1 and P of U1. Okay, so we're going to put the think about the P's power here. Okay, so this think about this W1P function. But however, first things we want to look at is how do you know this function in this space, right? And so what is the restriction on alpha here? Has to be. Now, first question is actually first we want to answer a more elementary question, which is that think about this function. So whether this function in the LP is in the LP1, even in this case, you can see that there must be some restriction on alpha. Okay, so we're going to find out. So let's do some calculation to see for which alpha and this function is in LP. So let's consider the integrations from B1 and 1 over x alpha, then times the P. Okay, so this is a dx. Let's put dx here. So we're going to think that for what alpha and this integration is finite. And you can use, because it's a two-dimensional case, so you can use polar coordinates. So it's easy to use polar coordinates. So this like gives us 0 to 2 pi and 0, 1. Okay, and in the polar coordinate, turn into polar coordinate, you have times r, right? dr. Then here, then the function itself can be written as r, and so you will have to have the absolute value inside here. So this is just the r, then r alpha p, then d theta. Like this. Okay, so there's nothing. So this function is independent on the theta. So therefore, it can be written. So the outside integration is basically a multiplication by 2 pi, and then the integration from 0 to 1. Then you can see which is r, then 1 minus alpha p and d theta. So you have to integrate this function from 0 to 1. So the question is when this integration will exist, and which is finite. And we remember there's a result about this, right? So I will record the result here. So the result is, suppose you have 0 to 1, 1 over x, let's say s. So this actually become improper integration, and this guy is less than plus infinity if what? What is condition on s? S has to be less than 1. So that's the condition here. So we use this result here. So this one is 1 over, so this can be written as 1 over r to the power alpha p minus 1. So you need, so alpha p minus 1 is less than 1. So that condition. So this condition is simply saying that the alpha has to be less than and 2 divided by p. So once the p is given, then alpha has to satisfy this condition in order for this function is in LP. we're not talking about the W1P yet. We haven't looked at the derivative. If you want this guy to be in LP, alpha has to satisfy this condition. Okay? So now let's see, look at the derivative here. So we do a similar computation, okay? So let's look at the formal derivative here. So let's say djf is equal to 1. So you can differentiate in x variable in the xj direction. So this is a minus alpha, then 1 over. So here you can verify this computation by itself, okay? Alpha plus 1 times xj divided by another x absolute value. So that's the derivative. So away from 0, so this is the derivative, which is equal to minus alpha xj and x alpha plus 2. Okay? Okay, so we want to look at the derivative, the estimate of derivative. So this means that you do this integration again, d1, then you have to dj to the p's power. The p's power. We want to see that when, for which alpha, this guy is also finite. Okay, so this one, which can be written, obviously it is bounded by alpha. Okay, and then you can see this function can be written as this things times this things, right? And this things, if you take x value sign on this one is controlled by 1. So therefore the whole thing is controlled by this b1 the 1 over x, no, here is p, but anyway it's a constant. So alpha plus 1 to the p's power dx. Okay, so you can continue to estimate. So this is less equal than alpha p, and so turn this into the polar coordinates, 0 to 2 pi and 0 to 1. Then you have an r, so r dr, then you have an r alpha plus 1 to the p, like this, then desay that. Okay, so you can see that this is equals to alpha p. Okay, the first integration 0 to 2 pi, you will become 2 pi. Then you have 0 to 1, and then your r, then you have 1 minus alpha plus 1 p dr. Okay, so here this will give us some conditions for which the derivative also in the LP space. Okay, so this one you can compare to this result. So what is condition on the exponents in order for this to be finite? The condition is that the negative of this is smaller than 1, right? So it's become alpha plus 1 times p, and then minus 1 is less than 1. So this condition basically says that if you put minus 1 to the other side, then you divide by p, you'll get similar to that, but you have a 1, additional 1 here. So you move that additional 1 to the right side. So this condition means so alpha is less than what? Less than 2p minus 1. So that's a condition will guarantee the derivative to be in LP space. Okay, the derivative. And so as far as you choose to consider this a LP space, you don't care whether it's the infinity or not. It's just the LP functions. Okay. Now if you look at these two conditions, you can see that the first condition, the second condition will imply the first condition. Okay, so because if this alpha is less than 2p minus 1, certainly it will be less than 2p, right? So this first condition, the second condition will imply the first condition. So therefore, we are going to use the second condition only. Okay, because we need both, and this will imply the first one. Okay, but that's not enough. We have to look at the boundary term. Okay, so let's do another calculation. So now you see we begin with the same scale. So let's say that I'm going to cover and this by a small circle, and with radius equal to epsilon. So this is called b epsilon, small c. Okay, so therefore you take the derivative dj and f and the phi. That's the testing function. And integrate on the b1 minus the b epsilon. Okay, do the same thing argument. And then you use the divergence theorem. So this will becomes the integration on the b, will be the boundary of the b epsilon. It's the boundary of b epsilon. Okay, and equals to the fj of phi, then mu j, right? Yes. So that's the result. So this is the term we want to estimate. So in the previous example, you can see that this right term goes to 0. So that will imply the result, right? Imply the result. So therefore, we need to also show that this guy goes to 0. That's the main question. If I can show that this guy goes to 0 as epsilon goes to 0, then we're done. Okay. So let's look at this term. So this term is basically fb mu j. Yes. So you can see there are a couple of things you have to pay attention. You see, phi is a testing function which is bounded, and mu j is less than 1. So therefore, these two terms, if you look at these two terms, and we can throw away because this is a just bounded term. The only term which is not bounded is f. So f in this case equal 1, equal this, right? It's equal to 1x alpha. So that term is not going to be cannot throw away. So this is less equal to bounded m term. M is a constant bounds the phi times mu. Okay. Then you have the integration of this, and the f is given by that. So there's 1 over x alpha, and that's it, and ds. All right. Okay. And then we'll continue this using polar coordinates. So this is equals to the m, and in the previous example when we did computation, we automatically assume that this is dimension 2. Maybe I didn't indicate clearly at the very beginning. We think that omega is Rn, but in the calculation we have assumed that this is the R2 case, and the only difference is that when you consider the boundary term, you have to turn this into polar coordinate. Okay. Now in the Rn case, you have to turn into the multi-dimensional polar coordinates. Then you can do the same thing. Okay. All right. So here you can see that this is equal to this, right? So therefore, this is less using polar coordinates here. So 0 to 2 pi. And then you have 0 to 1. Now the radius is actually, and yeah, have to be. So this is a small ball which really equal epsilon. So it's like you have to write epsilon here. Okay. So then you can see that this is a 1 over and r. And alpha, right? And ds. It's like this. Okay. Oh, there's another r here. Because this you're using polar coordinates, okay? So therefore you can continue from here. This is equal to m, okay? Then times 2 pi as usual. And then you have integration as 0 to epsilon, then r, and and 1 minus epsilon. It's 1 minus epsilon, okay? And so see, whether this is a finite, okay? Whether this goes to 0 actually. And you can see that this guy, so in order for this to be finite, you can think about this integration, 0 to 1 for instance. 0 to 1, if you replace this 0 to epsilon, replace this to the, this alpha. Okay, suppose this goes 0 to, instead of epsilon goes 0 to 1, then this condition for this function to be finite is what? This has to be, so the condition is 1, the condition has to be alpha minus 1 is what? This, yeah, sorry, I have to, yeah, sorry. I have to do, so I cannot use that shortcut. I have to do the real calculation. So this is equals to, okay, 2 pi m, okay, no problem. Then you integrate this guy. Now, if you integrate this guy, that you can see that this is going to be it's a 1 over, so 1 minus alpha plus 1. Okay, so this one will be r, and 2 minus alpha. Okay, this is using integration, the power rule, and then you have epsilon to 0. So all these are the constants. All these are the constants. So it all depends on these things. It depends on these things. So therefore, you can see that this has to be equals to hold on a second. This something is wrong. So this will become the epsilon 2 minus alpha, okay, and this will become, so minus the 0. So alpha is obviously less than 2, definitely. So therefore, so you are minus a 0. So this is the whole thing equals to epsilon 2 minus alpha. 2 minus alpha, okay? And if this is epsilon minus 2 alpha, and you can see that this goes to 0 as long as alpha is less than 2. As long as this is true. Okay, so now the question is whether this is true. So you have to summarize the previous condition. So when we want this f to be LP function, I need this condition, right? And then we need the derivative in the LP function. So we need these conditions. Now we see that in order for this game to work out, so you can see that we need this guy to be less than 2. But obviously this condition is also implied by this. Okay. Actually, you can see that from here, it's not only less than 2, this guy alpha has to be less than 1. So this condition is sufficient guarantee both conditions. So this is our condition, the final condition of alpha. As long as alpha satisfies this, and then you can see that you're going to have that. So then you can see that I can pass the epsilon goes to 0. Then I can pass the epsilon goes to 0. Then the epsilon goes to 0. And then you can see the integration of B1, the f dj b, and this will exactly equals to minus b1, then dj f, and the b. And you can see that the both function here, the f, with that condition, you can see both function f and djf, they are both in the LP. They're both in LP. So this means that, so this implies that our function f is in W1P, W1. So this prove that. So with the power P here, if we want to argue these things in the LP sense, then the arguments are a little bit more complicated. But basically, it's follow the same line. The line. So the key is you first you cover this best point by some small set, then you remove it later, let the epsilon goes to 0. Okay, so this is actually the second example we're going to talk about today, and I think today we are going to be just look at these examples. Okay, and next time I'm going to return to the general case, and we want to talk more about the multi-dimensional solid space, and then begin to prove some additional result, some new result. Okay, all right, so that's it for today.